Designing a vehicle to drive on the lunar surface was a monumental engineering challenge that pushed the boundaries of human ingenuity. It wasn't just about building a car, it was about creating a collapsible, lightweight spacecraft on wheels that could survive one of the most hostile environments known to man. To understand how we went from walking a few hundred meters to driving kilometers across the lunar landscape, we have to look at the incredible story of the Lunar Roving Vehicle. This is the complete breakdown of how it was built, how it was packed into a tiny triangular bay, and the high-stakes mechanical ballet required to unfold it on the moon. For decades, science fiction writers had dreamed of lunar transport, but for NASA engineers in the 1960s, it was a practical necessity. During the early Apollo missions, specifically Apollo 11 and 12, astronauts were severely limited. Clad in bulky, pressurized suits, walking was exhausting and slow. On Apollo 12, the astronauts could only venture a few hundred meters from their lander, essentially just a few city blocks. Every rock sample they collected and every piece of scientific equipment they deployed had to be carried by hand. By the time Apollo 14 rolled around, NASA tried a hand-pulled cart nicknamed the rickshaw, but dragging it over craters and through thick lunar dust was incredibly fatiguing. If we wanted to see more of the moon, we needed to drive. The constraints were unlike anything ever faced by a car manufacturer. The Lunar Module, or LM, had very limited space and weight capacity. Every kilogram sent to the moon cost a fortune. Initial designs like the MOLAB were essentially mobile laboratories the size of small trucks, but they were far too heavy and expensive. The solution had to be a vehicle that could fold up into a space no larger than a standard home refrigerator. NASA contracted Boeing and Delco to pull off this miracle in just 17 months. The resulting Lunar Roving Vehicle, or LRV, was a masterpiece of aluminum engineering. While it looked like a simple buggy, every component was optimized for the moon's 1/6 gravity. On Earth, the rover weighed about 210 kilograms, but on the moon, it felt like only 35 kilograms, light enough for 2 astronauts to lift it by hand if it ever got stuck. Despite its light frame, it was incredibly tough, capable of carrying 2 fully suited astronauts, heavy communication gear, and nearly 100 pounds of lunar soil samples. Perhaps the most iconic feature of the rover was its wheels. Standard rubber tires would have been a disaster, the vacuum of space would cause them to explode, and the extreme temperature swings would make the rubber brittle or melt. Instead, engineers developed a woven steel wire mesh. This mesh acted like a flexible tire, absorbing shocks while the titanium chevron treads provided traction over the fine, abrasive lunar soil. To ensure the mission never failed due to a mechanical breakdown, each of the 4 wheels was equipped with its own independent 0.25 horsepower electric motor. This meant even if 3 motors died, the rover could still limp back to the safety of the Lunar Module. Driving the rover was a surreal experience. Instead of a steering wheel or pedals, there was a single T-shaped hand controller in the center console. Pushing forward made the rover go, pulling back applied the brakes, and moving it side to side handled the steering. Because of the low gravity, the rover didn't handle like a car on Earth, it was prone to bouncing, and required careful maneuvering to avoid flipping over. The top speed was officially 18 km per hour, though the record set on Apollo 17 was just over 11 miles per hour. But the most difficult part wasn't driving, it was the deployment. The rover was stored in Quadrant 1 of the LM's descent stage. It was folded into a complex origami shape, held in place by pins and cables. When the astronauts reached the surface, they had to execute a perfect sequence to get it out. This involved a series of pull tapes and D-handles. As the commander pulled the release, the rover would begin to pivot out of its bay. Torsion springs, much like the ones in a garage door, provided the power to snap the chassis into its full length. As the frame straightened out, cables inside the struts would pull locking pins, causing the wheels to spring outward and lock into position. This entire process had to work flawlessly in a vacuum where no oil or lubricant could be used, as it would evaporate or freeze. During missions Apollo 15, 16, and 17, the LRVs performed spectacularly. They allowed astronauts to travel a combined distance of over 90 kilometers across the lunar surface. On Apollo 17 alone, Gene Cernan and Harrison Schmitt drove over 35 kilometers, reaching the edges of deep craters and distant mountain ranges that would have taken days to reach on foot. They found orange soil and ancient volcanic glass, discoveries that changed our understanding of the moon's history, all because they had the mobility to explore, even when things went wrong, like when a fender snapped off on Apollo 17, the astronauts used their ingenuity to fix it with duct tape and lunar maps. Without that fender, the rooster tails of abrasive lunar dust would have covered the astronauts and their equipment, causing them to overheat. Today, those 3 original rovers still sit on the moon, parked exactly where the astronauts left them over 50 years ago. They are silent monuments to a time when humanity didn't just visit another world, but we drove across it. As we look forward to the Artemis missions and the next generation of lunar terrain vehicles, we realize that the future of space exploration was built on the chassis of these incredible moon buggies. They prove that with enough engineering creativity, no terrain is truly off-limits. First we discovered Earth's liquid core, then we discovered a solid core within that liquid core, then we discovered that the solid core has bizarre properties that are more liquid-like. So is the inner core solid or liquid? The answer is yes. The mysteries of our own planet's interior have in many ways been harder to crack than those of the rest of the cosmos. I mean, we can send probes to the edge of the solar system and the 46 billion light-years to the cosmic horizon are largely transparent. We can see the most distant galaxies, but the 6,400 kilometers to Earth's center are both opaque to light and far beyond the reach of any conventional drill. The best we can do is to listen to the faint rumblings of distant earthquakes and then try to piece together how those seismic waves bounce around Earth's interior. To give you an idea of how seismology has lagged cosmology and the rest of physics, it was not until 1909, after Einstein's special relativity, that anyone realized that seismic waves could teach us about Earth's structure. It was Andrija Mohorovičić that noticed that some of the P waves, that's primary or pressure waves, found a shortcut from the earthquake's epicenter to seismic stations hundreds of kilometers away. He brilliantly inferred that the waves traveled through a denser and hence higher velocity region deeper in the Earth, thereby discovering the crust-mantle boundary that opened the floodgates in 1914, just a year before General Relativity and the following prediction of black holes. We discovered Earth's molten core. That was by Benno Gutenberg, who found that S waves for secondary or shear were blocked across a broad shadow region on the opposite side of the planet to their origin, while the P waves could make it straight through. Shear waves only propagate through solids, so he realized that this meant there must be a liquid interior to the Earth. But even those P waves play